So this is lesson 5, Newton's law of universal gravitation calculations. So in this lesson, we're going to calculate the gravitational force. We're going to learn that gravitational force depends on mass, and we're going to call those mass A and mass B. What we're going to learn is that mass and gravitational force are directly proportional. So if we double the mass of owl A, the gravitational force pulling on owl A and also the gravitational force pulling on owl B will both double. If we triple the mass of owl B, then those gravitational forces both triple. When you have a directly proportional relationship, the variables kind of copy one another. So if I quadruple the mass, the gravitational force quadruples. If I half the mass, the gravitational force halves as well. We're also going to learn that gravitational force depends on distance. So if I'm measuring the gravitational force between these two owls here, the distance that we're going to use is the distance from the middle of one owl to the middle of the other, and we call that distance r. We know that if distance doubles, the gravitational force will actually decrease to 1/4 of its original value. So we have sort of an inverse relationship going on here. When the distance gets bigger, the force actually gets smaller. They're acting as opposites. Now, I want you to notice a pattern here. If I was to triple the distance, the force would decrease to 1/9 of its original value. If I was to do 5 times the original distance, the gravitational force would decrease to 1/25 of its original value. So there's a square going on here, right? If I'm doubling something, that's changing it by a factor of 2. Well, 2 squared is 4. That's where this 4 comes from. If I do 5 times the distance, 5 squared is 25, and that's where I was getting 1/25 from. So in your notes, we're jumping down to the bottom of page 10 for a second to look at a formula. So the name for this formula is Newton's law of universal gravitation. And it says that any two objects, which we're going to call object A and object B, exert gravitational forces of equal magnitude but opposite direction on each other. So this formula here allows me to calculate the gravitational force between two objects, which really means it tells me what the gravitational force on object A is, and it also tells me what the gravitational force on object B is. And remember, A is feeling a force because of B, and B is feeling a force because of A. This is the gravitational force that A and B are exerting on each other. Okay, so in this formula, we have capital G. Capital G is what we call the universal gravitational constant. It's universal because it applies everywhere in the universe, not just here on Earth. And it's 6.67 times 10 to the negative 11. And then these are the units here, Newton meters squared per kilogram squared. That's on your formula sheet. The units of G are very useful because if you look at the units, it'll tell you what units you should be using when you use this formula. So the forces that you're going to get are going to be in newtons. Okay, MA is the mass of object A, and MB is the mass of object B. Both of those need to be in kilograms. And then R is the distance from A to B, and that needs to be in meters. And notice here it's R squared in the formula. So we're going to do a couple of examples, so jumping back up closer to the top of page 10. Example 1 is what I call a proportion problem, because you'll see when we read it, we don't actually know what owl A's mass is in kilograms. We don't know owl B's mass, and we also don't know what the distance is in meters. However, when we read the question, we'll see that we do know how these variables are changing. So we don't know what their values are, but we know how they change. So it says owl A exerts a gravitational force of magnitude 1.3 times 10 to the negative 10 newtons on owl B. Determine the new magnitude of the gravitational force if the distance between the owls is doubled and owl A's mass increases by 6 times. When you do a proportion problem like this one, you're going to identify the formula. So here, because it's talking about the gravitational force exerted by owl A on owl B, we want our formula from the previous slide. And this formula has 4 variables in it: G, MA, MB, and R. What we're going to do is we're going to list how each of those variables changes. Anything that doesn't change is going to be assigned a 1. So capital G is a constant. It is the same in every question that you do. Anything that doesn't change gets a 1. So G is being assigned a 1. MA, the mass of owl A, that increased 6 times. So I assign it a 6. MB, the question doesn't mention it changing, so I'm going to put a 1 with it. And then R is doubling. So we're going to assign R a 2. What we do is we go into our formula and we replace each variable with the number that we assigned to it. So G gets replaced with a 1, MA gets replaced with a 6, MB gets replaced with a 1. Then on the bottom we have 2. So that's where this 2 here came from. Okay, but it's 2 squared because it's squared in the formula. So in your calculator, if you do 1 times 6 times 1 divided by 4, because 2 squared is 4, you're going to get 1.5. And what that means is that the new gravitational force is 1.5 times the original force. So that's why I'm doing 1.5 times 1.3 times 10 to the negative 10, and that gave me 1.95 times 10 to the negative 10. Now, in the original question, the force only had 2 significant digits, so I should have actually rounded my answer here to 2.0 times 10 to the negative 10 newtons for my final answer. These values here, the 1, 6, 1, and 2, they do not count towards significant digits because they're not measurements, they're exact values. So example 2 is another proportion question. So the same number here is at the beginning. So owl A exerts a gravitational force of magnitude 1.3 times 10 to the negative 10 newtons on owl B. But this time owl A's mass increases 3 times, owl B's mass decreases 2 times, and the distance between the two decreases 3 times. What is the new gravitational force? So we're approaching it the same way. G didn't change, so we assign it a 1. Mass of owl A increases 3 times. So this is like saying the new mass of owl A is 3 times the old mass of owl A. So that's why this is a 3. Now, owl B's mass decreases 2 times. So that's like saying the new mass of owl B is half of its old mass. So that's why we had to put 1/2 here. And then the new distance between the owls is 1/3 the old distance. That's the same thing as decreasing by 3 times. So again, I'm going to replace the variables with the numbers that show how those variables change. So up top I have the 1 from G, 3 from MA, and then the 1/2 from MB. And then on the bottom I have 1/3 from R, but it is squared. When you square 1/3, you get 1/9. So then what I'm doing here is I'm just simplifying. So up top I have 1 times 3 times 1/2. That did not change, that's still right here. But then see how I have a fraction within a fraction. So I have a large fraction here, and then this 1/9, that's a smaller fraction within the larger one. When you have a fraction within a fraction, you can do kiss and flip. So this division here, that turned into a multiply, and then 1/9 flips, so it becomes 9/1, which is really just 9. So when you do this, 1 times 3 times 1/2 times 9, you should get 13.5. So our new gravitational force is 13.5 times the original force. And you should try typing it in your calculator just to make sure that you get the same answer as me. And hopefully you get 1.8 times 10 to the negative 9 newtons. Now we're going to try one that's not a proportion problem. It's going to give us actual values. So example 3, what is the gravitational force acting between Dave, who has a mass of 80 kilograms, and Sally with a mass of 55 kilograms when they are standing 1.20 meters apart? So in green, I've just written down all of my variables there. Now it doesn't matter which one you call MA and MB, just assign values to them. So here I've done it this way where MA is 80 and MB is 55. And then I've got my formula here. So when I type it in my calculator, I get 2.0 times 10 to the negative 7 newtons. That's a really small number. So that force is small enough that neither Dave nor Sally is going to be able to feel it, but this amount of force is acting on each of them. Okay, now this isn't the gravitational force caused by the Earth on Dave, and it's not the force caused by the Earth on Sally. Instead, this is the force that Dave feels because of Sally, and it's also the force that Sally feels because of Dave. Now, what I'd like you to notice is you've got a number in scientific notation here. When I type that in my calculator, it's tempting to do this. 6.67 times 10 to the power of negative 11. The problem with what I've just done is, first of all, it's a lot of keystrokes, takes a little bit of time to type in, but the bigger problem with this is when you do it this way, the calculator doesn't know that this number is just one number. It actually thinks that the 6.67 is separate from the 10 to the power of negative 11, which is bad because when we do longer, more complicated calculations, we can actually end up with calculator errors due to that. So I do not want you typing your scientific notation into the calculator this way. Instead, you're going to type it in a different way. This E here replaces the times 10 to the power of. And the E button on your calculator is right here above the apostrophe symbol. So you're going to do 6.67. Then you're going to press the second button up in the top left, and then the comma or the apostrophe, and you should see an E. And now you're just going to type negative 11. And there we go. This is a better way of typing it because when you use the E, you're telling the calculator that this 6.67 and the 10 to the negative 11 are connected, that they're all one value. And it will help you avoid lots of calculator mistakes later on when we get to more complicated questions like the next one. So I know that it is kind of annoying to type it with the E if you're not used to it, but you need to force yourself to do it at first because it will save you a lot of problems later. So go ahead and try example 3 on your calculator, make sure you get the same answer as me, and then unpause the video and move on to the next one. Okay, so this is actually example number 4 in your notes. So it says, during a lunar eclipse, the Earth, Moon, and Sun are aligned. Using the data below, calculate the net gravitational force on the Earth. So because the question asks me to calculate the force on the Earth, I care about what the Earth feels. So the Earth is feeling a pull towards the Moon. So another way of saying that is the Moon is pulling on the Earth. And at the same time, the Earth feels a pull towards the Sun. So the pull of the Moon, I'm going to call that FG1, and the pull of the Sun, I'm going to call that FG2. So the Earth feels like it's being pulled in 2 different directions at once. And we'll see how to calculate those in just a second, but I just want to mention, I do not care about the forces that the Moon feels. So yes, there are gravitational forces acting on the Moon, but I'm ignoring them because the question doesn't ask me about the Moon. Same thing for the Sun. So we're going to go ahead and we're going to calculate FG1, which is the force of the Moon pulling on the Earth. Because it involves the Moon and the Earth, you'll notice here I'm going to use the mass of the Moon, the mass of the Earth, and then this distance here will be the distance from the Moon to the Earth. So you'll notice there's a lot of scientific notation here, so we should be using the E button. So 6.67 times 10 to the power of negative 11 times 7.35 times 10 to the power of 22 times 5.97 times 10 to the power of 24 over 3.84 times 10 to the power of 8, and we have to square that one. So I get 1.98, and then the number keeps going, times 10 to the power of 20. This is not our final answer. So when we reuse this number in a second, we will not just use 1.98, we'll use all of this from my calculator, and I'll show you a little trick. To avoid having to retype this number multiple times, we can store it as a letter. So I'm going to press the store button here, and then I'm going to store it as letter A. So I'm going to hit alpha, and then A. And now, anytime I want to use that number again, I just have to press A, and up it comes. Okay, so now I'm going to calculate Fg2. So Fg2 is the force of the sun pulling the Earth. So it's the same formula, but this time it's going to be the mass of the sun, the mass of the Earth, and then the distance from the sun to the Earth. So let's do that. So 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 times 1.99 times 10 to the 30 over 1.5 times 10 to the power of 11 squared. And there we go, that's where the 3.52 times 10 to the negative 22 came from. Again, I'm going to store this number so I can find it easily later. I'll store it as letter B. So we've found our two forces individually. Okay, we've calculated Fg1 and Fg2, but the question asks us to get the net force, which really means the combination of the two forces. There's two different ways to calculate net force. So the first way is just to do the bigger force minus the smaller force, because really what net force is it's how much force is left over. Think about for a sec, if you had 10 newtons to the right and 2 newtons to the left, the net force would be 8 newtons to the right, wouldn't it? Because 10 minus 2 is 8. 8 is how much is left over. So we can do bigger minus smaller, which is what I did down here. So the bigger force was B. So I'm going to do B minus A. And that gives me 3.5 times 10 to the 22. Now to get the direction, when you do the bigger minus smaller method, the direction is just the direction of the bigger force. So because the bigger force was Fg2 and Fg2 points to the right, that's where I got to the right from. The other way to do this is you can remember that a net force is really the sum of the forces. So it's going to be Fg1 plus Fg2, but if you do it this way, you have to use direction. So you have to say, okay, well, Fg1 is to the left and Fg2 is to the right. So really what we're going to do is we're going to say, okay, well, Fg2, that's what I was calling B, and we're going to add A to it, but because A, which is Fg1, is to the left, we're going to make it negative. And when you do that, it's really the exact same thing. You get the same answer. So you can use whichever method you prefer, as long as you get the right answer in the end. Okay, example number 5. So again, we're going to calculate the gravitational force on the Earth. However, look at how things are lined up now. The moon is up here, sun is down here, and we've got kind of this L shape. So now Fg1 is pointing up because the Earth is going to be pulled towards the moon, and Fg2 is still to the right because the Earth is being pulled towards the sun. But if I want to find the net force, I need to combine Fg1 and Fg2. Now, up here, when I was combining Fg1 and Fg2, I just subtracted them. And that's because everything was in a nice straight line. However, here, things are not in a straight line. So combining the forces isn't just a matter of adding them or subtracting them. Instead, we have to do a vector addition. So check it out. I've actually lined up Fg1 and Fg2 tip to tail. Fg1 still points up in both diagrams, FG2 still points right in both diagrams. I've just redrawn them here so that they are tip to tail right there. And then this dotted line is the resultant, which is really F net. So to calculate F net, we're really just doing a squared plus b squared equals c squared. And so F net is this. So it's the square root of a squared plus b squared. And that is where the 3.52 times 10 to the power of 22 came from. And then we also need to calculate the angle because force is a vector, so we need to know what the direction of that force is. You're going to want to just make sure that you are in degree mode when you do this. And we're going to do tan inverse because we have the opposite side and the adjacent side. So tan inverse of FG2, which I was calling B, over FG1, which I was calling A, should give me the angle, and so I get 89.677 degrees, which I've rounded here to 89.7 degrees, and then we are east of north there.